In history, I'd say the singular most important discovery was that light is constant to all observers. To elaborate, imagine you are standing still and watching a car moving past you at 10 meters per second. You observe that car to be moving at 10 meters per second. But let's say Timmy is running at 5 meters per second in the same direction as the car. He would see that the car to be traveling at 5 meters per second. That makes sense, right? But that is not how light works. Einstein says that light will travel at the speed of light no matter how fast you are moving. Einstein came to this conclusion because of the inconsistencies of classical physics. Two main things were the results of the Michelson-Morley experiment and Maxwell's equations. Maxwell's equations of velocity of electromagnetic waves did not depend on the motion of the observer, meaning that the speed of light will not change even if you change the velocity. The Michelson-Morley experiment was to test if the speed of light changes depending on the direction of where we point the light. If classical physics were true, if we point the light in the direction of Earth, we will measure a slower velocity than if we point it in the opposite direction. Because of these reasons, and probably some other reasons, Einstein thought that light had to be constant for all observers. This fact led to Einstein's theory of relativity. In 1905, he published a paper on his special theory of relativity, and around a decade later, he finished his general theory of relativity. His equations improved on Newton's equations as Newton's theories fails to predict when extreme sounds and masses are involved. Of course, initially people questioned his theory, but around 1910 it became widely accepted. And it had held up as the most reliable theory of the universe as time went on and as tests were done that proved its validity. Tests that include atomic clocks that proved time dilation, and in 1919, during a solar eclipse, the results of a experiment proved that gravity bent light. Relativity theory also birthed multiple other fields of physics, most notably quantum mechanics. Einstein's theory introduces many new concepts, such as relativity of simultaneity, time dilation, length contraction, speed limit, and the mass-energy equivalence. But the main topic that we need to focus on that is related to interstellar travel is the speed limit. To understand the speed limit, we first need to understand what starts to happen when we approach the speed of light. Let's say there's a person that is traveling really, really fast. To everyone else, the time for that person is slowing down, but to that person's perspective, everything else is speeding up. Time dilation can be explained using a photon clock. So here, photon clock is two mirrors and a photon bouncing between them. This is how you would see a photon clock if you are going at the same speed as it. So imagine you are in a spaceship with the photon clock. This is what you would see. Now, if the spaceship is moving really fast, this is what a stationary observer would see, since the photon clock is also moving horizontally. Now, here you can see that the path of the photon is longer as it is diagonal. And since the speed of the photon never changes, that means that the time it takes to travel this distance takes longer. So therefore, time on the spaceship would seem to flow slower. So how do we get gamma? We get gamma by deriving it from Pythagoras. It's not a very hard thing to do. Here, hypotenuse is S, and that's just Pythagoras, and L equals to this because d over t equals v, and d is just the length. Here, if we say if L equals to that, then in this equation we can just replace L with that to get this. So we say 2s equals over c equals t because again this is just this rearranged. D is this length and t is and v is equals to speed of light. We say s equals to this, therefore we can just replace s with this to get this. We get to this step by just squaring both sides to get this, of course, and then to get to this step, you just do more simplifying. We say delta t0 equals this because delta t0 is when velocity equals to 0, and this plus 0 is just this by itself. So we can replace this with delta t0 to get this equation. Here, this is just the same thing, nothing special. We just factor out delta t squared, do some rearranging. And we get this by doing some more rearranging and square rooting, and we end up with t equals to gamma t, where gamma equals to this. Here, according to my calculations, to experience 2 times time dilation, you would have to be traveling at 2.6 times 10 to the power of 8 meters per second. So how does time dilation make it that we can never see something moving faster than the speed of light? So let's say there is a spaceship that accelerates at 1 million meters per second. Initially, from rest, we see it, accelerating at 1 million meters per second. Pretty simple. Now, when it gets up to a velocity where, let's say, gamma is 2 and time dilation makes so that every 1 second spent on the ship is actually 2 seconds from a stationary perspective. That means that for the person on the ship, they still see themselves accelerating at a million meters per second, but since 1 second on the ship is 2 seconds for a stationary perspective, for the person that is stationary, they actually see the ship accelerating at 1 million meters per 2 seconds. So in the ship example, we see that the ship is moving at 1 million meters per 2 seconds. That is the same as saying that it is moving at half a million meters per second. So that means that for the stationary observer to to measure the acceleration of the accelerating object, we can divide its acceleration by gamma. Here we have time dilation graphed against velocity. We see that as velocity approaches the speed of light, we see time dilation approaching infinity. And since we know that how we view the acceleration of a object is the acceleration of the object divided by the time dilation it experiences, since it approaches infinity, the rate of acceleration will approach zero as it approaches the speed of light, meaning that it will never accelerate to the speed of light. So time dilation makes it so that a stationary observer will never see a spaceship moving faster than the speed of light. But why won't the person inside the spaceship see himself moving faster than the speed of light? This is because of length contraction. Length contraction makes it so that he views the distance he travels getting shorter and shorter, while the time it takes to travel that distance staying the same, meaning that he will see his velocity getting slower and slower. This will make so that he will never see himself moving faster than the speed of light. This graph represents the amount of kinetic energy needed to travel certain velocities. So as velocity reaches the speed of light, we see that the kinetic energy needed approaches infinity. So what does this all mean for interstellar travel? This means that, of course, we will never reach the speed of light, meaning that it takes really, really long to get to places. But the good news is that for the let's say you're going really, really close to the speed of light, for the people on the spaceship, they will experience so much time dilation, it will actually take like not that long for them to reach their destination. The only problem is that for the people on Earth, it will take really, really long. So yeah. Another limitation is that space is expanding faster than the speed of light. So 97% of the observable universe is actually out of our reach, and we will never be able to get to them.